started? Let's get started. So, at the end of class the other day, we were talking about pKa trends among amines. Just let me do a quick review of what we talked about towards the end, and then we'll get towards more pKa trends, and then some real chemistry shortly. So, we're talking about pKa trends, and in general, the more substituted your amine is. So, the more carbon-based substituents, sp3 carbon-based substituents off of your amine, the higher pKa the conjugate acid of the amine will be. So what that means is, the more substitution you have on your amine, the more basic the amine will be, because of course a higher pKa means you're more basic. And we discussed why more substituted, so primary and secondary amines are more basic than ammonia itself. And the reason was the same reason why tertiary carbocations are more stable than secondary carbocations, which is this idea of hyperconjugation. So with the typical carbocation, the substitution of that carbon, right, if it has a hydrogen, the lone pair of electrons of the hydrogen can donate to what we call hyperconjugation into the empty p orbital of the carbocation, stabilizing the carbocation. And the more substituents you can have that can do this hyperconjugation, the more stable. So that's why a tertiary carbocation is more stable than a primary, it's because we're putting electron density into the empty p orbital. And so what that means with amines, you can think of this two ways. First, when you have the ammonium, so the ammonium is the conjugate acid of the amine, when you have the ammonium, the substitution off of the ammonium can do this hyperconjugation effect, slightly putting some of the electron density from the carbon-hydrogen bond towards the positively charged nitrogen. So in essence, slightly stabilizing the positive charge of the nitrogen by throwing some electron density towards it. All right, and so that is going to stabilize the acid, and a more stabilized acid is going to be less acidic, and so that's why we see the slight jump in pKa. It's about tenfold. Yeah.
When we were talking about conjugation, are we talking
hyperconjugation, but not conjugation?
Hyperconjugation. Are we considering electron as a weight, and then when they're forming a bond, we're considering electron as a particle?
A little bit about the scope of this class. I've never thought of it that way, but I guess you could. I guess you could think of it as a weight, but just think of it as some of the minus charge from the carbon-hydrogen bond donate, so electron density from that bond donating towards the positive charge. It's a lot more clear in this case, right? But it's the same idea, that there's some the electron density from this bond is distorting, so there's more electron density and partial minus charge towards the positive charge and the nitrogen due to a Coulombic stabilization. The other way you can think about it, about why more substituted amines are more basic, perhaps a little more simply, is you can say, well, here's our amine, so this is the ammonium, this is the amine, and we can have, again, this hyperconjugation event putting more electron density towards the lone pair of electrons. What is putting more electron density towards those lone pair of electrons going to do to those lone pair of electrons? Stabilize or destabilize? Destabilize. And so a lone pair of electrons that's destabilized is going to be more basic because they're higher in energy. And so they're going to want that proton. So in other words, the carbon substitution slightly destabilizes the amine form, while it is also slightly stabilizing the ammonium form. And so that is in essence why more substituted amines are more basic. So it's this very subtle, albeit we're talking about a pKa difference of 1.2, which means it's a little bit greater than a tenfold effect. So maybe we shouldn't call it tenfold effect, subtle. But yeah, it's a 1 pKa unit effect that this substitution puts on this thing. So more substituted amines are more basic because, at least they're more basic in gas phase experimentally because of this effect. So hyperconjugation, the same idea as this. And so, this isn't the most simple thing, but I think most of you guys will look at it and be like, all right, I can see where he's going with this. Just remember, more substituted amines are going to be more basic. And then I threw you guys a curveball. And I took aniline. So benzene with a nitrogen group off it. And I asked you guys on Monday, is aniline going to be more or less basic than a typical mono substituted amine? And the majority of the class, on Monday said it was going to be more basic, and then I told you guys it's actually going to be less basic. And why is it going to be less basic? And so I told you it was a resonance argument, which is true. But first and foremost, I forgot to mention the most obvious thing. This nitrogen in the aniline, what's its hybridization? sp2. This is an sp2 nitrogen. So what does sp2 nitrogen mean? Well, it has more S character. What does more S character mean?
More stable.
It means it's closer to the nucleus. So minus charges are going to be more stabilized. Or lone paired electrons is going to be more stable because it's closer to the nucleus. All right, so what do you think will happen when you have a positive charge in an sp2 atom? Will that be more or less stable than the positive charge in sp3? It will be less stable, right? Because a positive charge is being closer to the positively charged nucleus. So coulombically speaking, opposites attract, the same charges detract. So now since you have an sp2 nitrogen that has a positive charge, now that positive charge of the nitrogen is actually closer to the positively charged nucleus. And so that's going to mean this positive charge is destabilized. And when you have a destabilized conjugate acid, what does that mean? Well, it means your acid's going to be more acidic. So your ammonium is less stable, meaning it's more acidic, yes.
You're talking about the positive charge in the nitrogen and the carbon?
No, in this case, the positive charge on the nitrogen, right?
And which one is the other?
There wasn't another positive charge.
I thought you were talking about.
No, I wasn't.
Sorry.
Just let me backtrack. So I was talking about going from aniline to an amine to the ammonium salt of aniline, saying why is this so much more acidic, 5 orders of magnitude than a typical primary amine? And that's because this positive charge is going to be less stable than this positive charge, because this is a positive charge in an sp2, and the more S character you have, the more electronegative you are, meaning you want minus charges, but you don't want positive charges. And so what that means is because this is sp2, and the reason it's sp2 is because it can obviously resonate its lone pair of electrons throughout the system. When it becomes protonated, and a positive charge in an sp2 atom is going to be less stabilized than the positive charge in an sp3 atom. So because it's sp2 and it has resonance, the sp2 is going to be this is going to be a more acidic proton, meaning that the ammonium in aniline is less stable than the ammonium for a typical sp3 aliphatic amine. So this trend is actually kind of similar. Let's look at pyridine now. From the notes, or does anyone know offhand what the pKa of pyridine is? 5.2. So pyridine is basically a very similar pKa to aniline. And it's really, on a first analysis, it's the same idea. It's the lone pair of electrons on pyridine the nitrogen is sp2. So the same idea when you form the pyridinium cell, so the ammonium version of pyridine, again, it's your positive charge is now in an sp2 nitrogen and sp3. So that's why pyridine, and so since it's sp2, it's going to be closer to the positively charged nucleus, and thus it's going to be a less stabilized positive charge, meaning that the ammonium or the pyridinium is going to be more acidic, because a less stable acid is a more acidic acid. A less stable acid is a more acidic acid. And so since these two sp2 ammonium salts are sp2, they're less stable and hence more acidic. Another way, at least to think of aniline, and so since aniline is a stronger acid in its ammonium form, that means it's a stronger or weaker base. Is aniline a stronger or weaker base than a typical primary amine? It's a weaker base, absolutely. And so you could in part say, well, it's a weaker base because its conjugate acid is a stronger acid. And so we talked about the effects of this being an sp2 being less stabilized, but you can also think about this being a weaker base from the amine form from just saying, in a primary amine, the lone pair of electrons is just on the nitrogen. It's over one atom. Whereas in an aniline, you can resonate the lone pair of electrons into the aromatic ring. So the lone pair of electrons of the aniline, instead of being in just one atom, it's across the entire aromatic system, so across 7 atoms. And so the lone pair of electrons, via resonance, is spread out throughout the entire system. And so if you have a spread out lone pair of electrons, it's going to be less high in energy and less basic because it's spread out over the system rather than localized in one single atom. So that's another way to think about why the aniline itself is less basic and more acidic. So pyridine has a pKa of 5.2. And again, this is the whole sp2 protonated form. It's sp2, so it's going to be less stable than sp3. What happens if we put another nitrogen in the system? So we call these pyridines with 2 nitrogens, we call them, not a lot of names, sometimes we call them pyrimidines or pyrazines, but it's a nitrogen with it's a pyridine with 2 different nitrogens. And so just for the first protonation, so protonation 1 of nitrogens, is the pKa of this going to be higher or lower than the nitrogen? So in essence, what I'm asking you is the second nitrogen going to be an electron donating or an electron withdrawing group? It's going to be an electron withdrawing group, right? Because the electronegativity argument. So knowing that the second nitrogen is electron withdrawing group, is this going to be more or less acidic than pyridinium? More. That's going to be more acidic, exactly. So the pKa of this is about 2.5. See, it's not that bad. Once you get this basic idea of sp2 versus sp3 and what's what, then I can make subtle changes like put in an electron donating or electron withdrawing group, and then you guys can say, tell me what's more or less acidic, right? Let's just talk about a couple other key heterocycles to be aware of that are amines. So first up, a review from the aromatic chapter. Which one of these nitrogens is going to be the basic nitrogen? So if you throw in an acid, which one of the imidazole nitrogens is going to be the one that's going to protonate first? The top one, right? Why? Well, what happens if you were to protonate this one?
Break aromatic.
Thank you. So because this lone pair of electrons and this nitrogen are involved in the aromatic system, these electrons are not acidic, are not basic at all, whereas these, which are orthogonal to the aromatic system, are basic. So what we would initially form would be this imidazolium, where we protonate this nitrogen. And what do you think this pKa would be? Would this be more or less? Yes. These protons are less acidic than pyridinium and less acidic than this guy. And that's actually because even though these lone pairs of electrons are indeed in the aromatic system, they can donate the electron density into this system via resonance without losing aromaticity. Now giving us this resonance structure, which is an equivalent resonance structure as drawn, right? This resonance structure and this resonance structure are identical because of the symmetry in the imidazole. And so because we have this equivalent resonance structure, the positive charge, or the acid, it's stabilized to a degree. And so typically the pKa of an imidazole is typically about 7. I don't have it in my notes, but that's usually what we quote, is about 7. But then, of course, if we were to do a second protonation, what would well, let me do pyrrole. And then, of course, again, this is also reviewed from the aromaticity chapter. What would the pKa of a pyrrole amine be? High or low? Low, very low, because again, in this case, we break aromaticity. So then again, the pKa of pyrrole is 0.4. So I'm going to box the ones I feel are most important to try to know well. Try to know these trends and realize that I might give you an example where I might put some kind of substitution on one of the rings, like an electron donating or electron withdrawing group, and be able to ascertain, based on what you know of electron withdrawing, electron donating groups, how that will affect the pKa of the ammonium associated. Yeah?
Pyridine example?
Yeah.
Can you say again which one was electron donating or electron withdrawing or whichever one?
Wait, for this one?
No,
Or
the next one.
this one?
Yes.
So the second nitrogen is electron withdrawn because of electronegativity.
The one that doesn't get protonated?
Yeah, exactly.
Electron withdrawing.
Yes. However, again, in the imidazole, so in this case, we can't do resonance because the lone pair of electrons in this nitrogen is going to be orthogonal to the aromatic pi system, so it can't resonate. Whereas in the imidazole, the lone pair of electrons, we know, takes place in aromaticity, which means it has to be parallel to other pi systems. And because it's parallel to the pi systems, it can partake in resonance, thus stabilizing the positive charge, explaining why the pKa is greater, like 7 rather than like 5.
So on the other one, it can't because
Exactly.
they're-
And the other one, again, this is review of chapter 15, is the way the system is, both of these lone pair of electrons are going to be in the plane of the molecule, meaning they're going to be perpendicular to the pi systems. So they can't do aromaticity because they don't overlap. Whereas in the imidazole, because the lone pair of electrons this lone pair has to take place in resonance, we know it is parallel with the pi systems and can participate in this resonance I draw here. And this resonance stabilizes the imidazolium positive charge, explaining why it's more basic, i.e. less acidic than pyridine, even though it's still an sp2 nitrogen. It's got that electron donating. So in this case, when you have resonance, the second nitrogen acts as a electron donating group. When you don't have resonance, the second nitrogen acts as a electron withdrawing group because of electronegativity. All right, let's talk about the chemistry now of how to make amines. So, can someone tell me what they think the most simple way to make an alkylated amine? So, to take ammonia and make a primary amine. What would be the most simple way to do it?
After you apply an amide, right?
Amide or an amine? Or by amide, do you mean like a negatively charged amine, or?
I mean, like, I think I mean NR2.
Yeah. All right. So an amine, a normal amine. You're saying let's take, and you said NR2, so let's draw NR2. But we could, in theory, we could do this with any amine, any sp3 amine. We could do this with. But I'll do NR2. So you take your disubstituted amine, you take your alkyl chloride, I'm going to do methyl iodide because why not? And then you can do an SN2 type reaction. And of course, in this case, this will give me an ammonium. And it looks good in paper, right? This looks like a perfectly good synthesis in paper. Can someone tell me any possible issues with this synthesis? Oh, well, let me point this out. So, in the very, very early stages of the reaction, so after the first 20 molecules of, 1 times 10 to the 26 react, right? You'll have a little bit of this, but you'll have a lot of your starting material, right? Is it reasonable to have another equivalent of your starting material come in, so just a second equivalent of your starting material come in, and in some kind of equilibrium, grab this proton, now to give your product in its neutral form, in its neutral form, plus an equivalent of the starting material now in its ammonium form. Is this a reasonable thing to say can happen? Absolutely, right? If you form ammonium, ammonium's got to, this and this are going to have similar pKa, so once you form this, there'll be some equilibrium probably equal to roughly 1 between your product in its ammonium form and your product in its amine form after protonation by another equivalent starting material. So yeah, I think it's fair to say that this can almost certainly form. So if this forms, what can this do that can throw a wrench in this perfectly good reaction? It can alkylate again. So, and it will. So then this will do another SN2. And to give you the dialkylated amine, all right, and so it will repeat this reaction just with the starting material doing it this time, and then give you a product that is resultant from the reaction going a second time. So we get an overreaction. So what ends up happening if you try to take an amine and do an SN2 with it is you'll get a mixture of your product plus the over-reacted product. So in other words, the amine just won't stop once. Because we can form the neutral amine in solution, the neutral amine will just go and attack the, your alkali iodide again. So you'll get a statistical mixture of, I'll draw it in this box. The final reaction outcome will be a statistical mixture of your ammonium, so your starting material in protonated form, your monoalkylated product, plus your dialkylated ammonium. So in this case, you'll get 3 different products. Whenever you have a reaction that gives you 3 different products, you say it's not a good reaction. So there's no selectivity. So that is why no one ever will alkylate an amine using another amine. The reaction's messy. You get overreaction, and by getting overreaction, that means you'll get half of your starting material not reacting at all because it's just protonated. And so and then by the time you might get unprotonated, you already used all your alkali iodide to make your dialkylated product. So you get a mixture. This is a giant CF, professionally speaking, from someone who's tried this reaction before in an NMR and seen 5 or 6 different products possible. So if you want to make an amine, do not make the amine by doing an SN2 with an sp3 amine and a alkali iodide. Does not work. So, if we know we can't use, so we know we cannot directly alkylate an amine. What we have to do, we have a couple options to make amines, and that's really what I'll be talking about really for the rest of this class before I hit the review session next week. So I'm going to start off with the way I make amines. If I have to make an amine in my lab, or one of my students has to make an amine in my lab, this is what I showed them to do in 2015. I have them start off with an alkyl halide, so nothing changes there. They're still using the alkyl halide, so it's still doing an SN2 type reaction. But instead of using an amine, I have them use an azide. So an azide is a nitrogen double bonded to another nitrogen, double bonded to another nitrogen. So we call this an azide. And so this thing I drew up with a sodium, a nitrogen with a minus charge, double bonded to a nitrogen with a positive charge, double bonded to a nitrogen with a minus charge. This is sodium azide. So N3 is an azide. So do you think sodium azide is nucleophilic? Yeah, it's got a minus charge on it. It's going to be about as nucleophilic as a nitrile. And so sodium azide is a great thing to do in SN2 using your typical SN2 conditions. 232 review. If you had to do an SN2, what solvent would you use? All right. Yep. Exactly. All right. And so then the resultant reaction of this will be what we now call an alkyl azide. So the azide replacing your bromine in an SN2 reaction, now giving us an alkyl azide like so. So this is just an SN2 mechanism, know that. And then the interesting thing about azides is you can do a palladium and carbon hydrogenations. Remember palladium and carbon hydrogenations for like alkenes from 232? So you can go from an alkene to an alkane using palladium and H2. Palladium and charcoal, an H2 will take a double bond to a single bond. Don't worry about the mechanism, but palladium and carbon and H2 will do this. Will do something similar to an azide, where if you take your azide and throw in palladium and hydrogen gas in a balloon, so it's kind of putting a hydrogen balloon, so it looks like a kid's birthday party. The product you'll get out will be your amine plus an N2 having bubbled away. So don't worry about the mechanism of it. Just realize that azide, which you can make using SN2 chemistry, plus palladium carbon H2 really nicely go to amines, primary amines. So this is nice in that it gives you a primary amine. So what if you wanted to make a secondary amine? Would this azide strategy let you make a secondary amine? Absolutely not. Here's how you make a secondary amine though. And it's through our favorite mechanism. So I had this amine I just made, and I throw in an aldehyde. If I take this aldehyde and this amine, what am I going to get out? An imine, right? This is going to get, the amine's going to condense into the carbonyl to give us an amine. So this is like the first step of the managed reaction we talked about on Monday. So the amine is going to add into the aldehyde, kick off water, eventually giving us our imine. And so, we know imines are reactive electrophiles. That's what we talk about in the managed reaction. And so they're electrophilic enough that you can take a little bit of H3O and then some sodium borohydride to reduce your amine, and under these conditions with H3O and a little bit of sodium borohydride, final product you'll get out will be the amine that comes from sodium borohydride attacking this. But my question is sodium borohydride going to attack the amine, or is the acid going to do something that will make this reaction go better?
Probably gonna do something.
Yeah, yes, it's going to permeate the amine, right? So kind of mechanistically speaking, it's going to grab the proton, giving us, I'll draw these boxes up here. Giving us this positively charged mini M. And then you can take your H minus source, so sodium borohydride, and it's just going to add in to your mini M. So the hydrogen from the sodium borohydride will be on the, what was the aldehyde carbonyl carbon to give us our secondary amine. And if you want to make a tertiary amine, you just add in 2 equivalents of sodium borohydride and 2 equivalents of aldehyde. So that is how I will have that's how I have my students in my lab make amines. Via a sodium azide SN2 to give us the azide, followed by a palladium and carbon hydrogenation of azides to nitrogens using H2. And then finally we form the amine, and then we reduce the amine using sodium borohydride. So not that bad, right? Like a lot of this chemistry is review, and frankly, if it was up to me, this would be the only amine synthesis I would teach. And this is a nice way to make amines, perhaps the most simplest way. Quick trivia question. So, could you do this chemistry with a secondary amine? So if I had a secondary amine doing an aldehyde, could I alkylate it?
Yes.
Absolutely. Would you need acid? So with a secondary amine, right? Right, so I just used pyrrolidine or something like that. And the secondary amine condenses in the aldehyde. Because it already has 2 substituents, the secondary amine is going to be the aminium by default, right? Do you guys see that? So since the secondary amine is going to give us an aminium by default, we don't need acid to reduce a secondary amine to the tertiary amine. This entire thing I just talked about, I'm going to draw out the last scheme, so the last amination in its own board because it's that important. We call reductive amination. Reductive amination. So once again, what you do is you take your amine, either a primary or a secondary amine, you take either an aldehyde or a ketone. So I'll do an aldehyde in this case, in the primary case, and a ketone.
Aren't those both primary amines?
Thank you. I really do write my notes before a lecture, but you guys see how often I actually look at them. So a primary or secondary amine, and you either take an aldehyde or a ketone. And maybe you just throw in a little bit of H3O as a catalyst to catalyze the imine formation. And then once you have your imine, you throw in your sodium borohydride. So that your H minus from the sodium borohydride will then attack the imine or iminium. Of course, for the secondary imine, it will attack the protonated version from the acid, since the protonated amine will be more reactive than the neutral amine. So then it attacks. Then I'll give you your amine, your now alkylated amine. And voila, you have a good general amine synthesis where you don't have to worry about overreaction. Does someone want to tell me why you don't have to worry about overreaction with reductive amination? Why do we not have to worry about over-amination? So why will a reductive amination just stop once?
Want to say steric effects of Sinoboldi?
Perhaps. The real thing is you form the amine once, right? You have to form the amine. If you can't form the amine, you're not getting a second step, and so a second reaction. And so think of it this way: we form our amine, and then we throw in sodium borohydride. The sodium borohydride is going to reduce the amines, right? But it's also going to reduce any leftover aldehyde we have. So basically, once the sodium borohydride comes into play, we won't be able to form the imine again because any of the aldehyde that could form the imine to give us an overreaction is going to be reduced as well. So it steps, so pretty much this reductive amination gives us a level of control where we can only have it react, we can only make it so it reacts once because in the conditions you can only form the imine once. So because you can only form the imine once and then you reduce it, once you reduce it, the sodium boro, so what's going to reduce first? Leftover aldehyde that hasn't formed the imine yet, or the imine? Leftover aldehyde is going to reduce pretty quickly, right? So let's say you use 1.5 equivalents of aldehyde, or a ketone. And so the first equivalent completely formed the imine, and the leftover 0.5 versus storing as the aldehyde. So when we throw in the sodium borohydride, in addition to reducing the imine, all right, it will reduce the imine to give us our amine, which could technically form the imine with the leftover aldehyde. But because the aldehyde is probably going to be more reactive towards a reduction, because aldehydes are some of the most reactive electrophiles we know towards sodium borohydride, the aldehyde is going to be reduced as quickly, if not faster, than the actual formed amine. So by the time we form our secondary amine, in this case, which could go on and react further, there's going to be nothing for it to react with. All right, and so because of that idea, we're able to get control and only get our monoalkylation to the reductive amination, rather than our di or trialkylation, which we get if we just use an sp3 amine. And again, mechanistically, it's just you form the amine, and your sodium borohydride reduces the amine. So it's chapter 17 chemistry followed by chapter 12 chemistry, with a twist. There's one more way to make a primary amine that does not involve azides. This is more of an old school method, but the book talks about it, so you should be aware of it. And that is the Gabriel synthesis. So the Gabriel synthesis takes phthalamides. Phthalamides, one of the funnest things to spell. So it takes this phthalimid. And so this is a nitrogen that's a bis amide. And so nitrogens, so things that have two amides after them, we don't call them amides, we call them imides. So you can imagine maybe imides the plural of an amide when you deal with it on the same nitrogen. So phthalamids are very acidic. Well, not very acidic, but they're quite acidic. So that you can use something like sodium hydroxide to deprotonate the hydrogen and the nitrogen. To give us this nucleophilic nitrogen.